Hi all, welcome back to the lecture video session on the different type of materials used for conductors for the transmission line system. In the previous video we were discussing about the high ampacity conductors, and in one of such very important type of conductor is the GTACSR, where we found that it is very convenient wherever it is used to operate the existing transmission lines, and simply we can replace the existing transmission line with the GTACSR, which could give us the double the power rating. So double the current carrying capacity of the transmission line. So actually there is no modification that is required for the towers also, and then hence it will not involve any kind of cost to change or to modify the existing towers or the supporting structures that will hold the conductors. Now let's move on to the another type of very important type of high ampacity conductor, that is GZTACSR, that is gap type super thermal resistant alloy conductor, steel reinforced. Figure shows the cross section view of that particular type of conductor, where we can see the gap is filled with the grease, and then it gives the extra high strength, and then it can move the thermal resistant alloy, and then the super thermal resistant aluminum alloy is surrounded, and this particular type of conductor is characterized by the extra high strength steel core at the center and surrounded by the aluminum conductors. Super thermal resistant alloy is supplied in the conductor part, and then to maintain the gap between the steel core and then the inner layer of aluminum, the inner layers are trapezoidal in shape, and the thermal resistant grease is also filled in the gap to avoid the friction between the steel core and then the aluminum inner layer. And the another characteristic of this is that the aluminum layer and then the steel core move independently, and there will not be any relative movement. So the higher ampacity is introduced because GTACSR can carry 1.6 times the higher current than the ACSR of equal size. So once this is characterized with a higher current carrying capacity, GZTACSR can carry around 2 times the higher current carrying capacity than the ACSR of equal size. So most importantly, GTACSR can carry 1.6 times higher current carrying capacity, higher current than ACSR of equal size. GZTACSR can carry 2 times the higher current than ACSR of equal size. So we understood that the inclusion of this, the thermal alloys increases the higher current carrying capacity. And the sag is also very less compared to compared to the ACSR lines. Now we can think about the other type of the higher ampacity conductor, that is thermal resistant aluminum alloy, ZTAI. TAI and then the ZTAI will improve the thermal resistant characteristics by adding the zirconium. As I already said that the zirconium is a very costly metal, but still it improves the characteristics of the conductor, and it can withstand up to 150 degrees centigrade, whereas the ZTAI can withstand up to around 210 degrees centigrade. The normal TAI can withstand up to 150 degrees, whereas the ZTAI can withstand up to 210 degrees centigrade. And when we think about the current carrying capacity, ZTAI can carry around 2.2 times that of the hard drawn aluminum, that is around it can carry around 2 times that of higher current. So special sagging method is also used in order to so that sag will not become a problem, and then because we need to apply the sag only onto the steel core. Now the next type is the bundled conductor, and why we need to use a bundled conductor. Bundled conductor is a conductor which is made up of 2 or more subconductors, and it is used in one phase conductor. So instead of using single conductor per phase, we are going to use the bundle conductor per phase. So the voltages that are more than 220 kV, it is always preferable to use more than one conductor per phase, which is known as the bundle conductor. So the bundle conductors that are used will provide the better regulation and then the higher efficiency, because it decreases the inductance effect and then the skin effect that is present in the straight conductors in the power lines. So what are the advantages of this bundled conductor? That is reduced reactance and then the reduced voltage drop, increased efficiency, better regulation, better voltage regulation, and reduced corona losses, highest critical disruptive voltage, reduced surge impedance, that is nothing but equal to square root of L divided higher critical disruptive voltage, and then when we think about the surge impedance, which is nothing but Z is equal to square root of L divided by C. So when we see this, higher the inductance, higher will be the surge impedance, and then if L is reduced, then the surge impedance will also be reduced, and reduced Z will allow the maximum power transfer. So the surge impedance should be kept as minimum as possible for a transmission line. So if we increase the capacitance, then also the surge impedance will become lower, and which allows the maximum power transfer. So to transmit maximum power, the bundled conductors are most suitable and they are used. And now after understanding the types of the conductors that could be used in different weather conditions and for different ratings, we can think about the supporting structures, which are the heart of the power transmission lines. So the overhead conductors are supported by the supporting structures, which should be rigid in nature, and the main components of this OH lines are conductors and then the supports. Now the support may be the poles or towers, depending on the type of the transmission line that it is going to support, and it keeps the conductors at the suitable places and then the suitable level above the ground. Now the insulators are also the major part of the transmission line system, which are attached to the supports, and then it insulates the conductors from the ground. And cross arms are also the part of the transmission towers, that is the supports, which provides the support to the transmission line conductors as well as the insulators. Now other than this, there are certain accessories which are miscellaneous items, and then these are phase plates are used, and then the danger plates are used, lighting arresters are used, spacers are used, anti-climbing wires are used, and these are all these comes under the category of accessories of a overhead transmission line, of a transmission system. So consider the line supports. There are different type of voltages that are transmitted. So obviously the line supports will be different for different type of overhead conductors where it is supposed to support. The supporting structures for the overhead transmission conductors are of various types of poles and the towers that are called as line supports. The general properties of the line supports is that it should offer the mechanical strength to withstand the weight of the conductor and the wind loads, and the height and weight without the loss of the mechanical strength, and it should be light in weight, and it should be cheap in cost, that is it should be cost effective, and it should not add on to the transmission line system, and it should be economical to maintain the larger life, and then it has to offer a good life to the existing system, and it should also be under the safety norms. And easy accessibility of the conductors for the maintenance should also be offered by the supports, and the line supports used for the transmission and the distribution of electric power are of various types, including the wooden poles which we saw in the earlier days, and then it got transformed into steel poles, and then concrete poles, RCC poles, and then the lattice steel towers which we are seeing for the different type of higher voltages and then the lower voltages. And here when we think about the supporting structure, the choice of the supporting structure majorly depends on the line span, cross-sectional area, the line voltage and the cost, and then the local conditions. Let's understand each type of the poles, starting from wooden poles. Wooden poles, there are A-type or H-type structures were used when we started with the wooden pole, and majorly it was used for the distribution side, and then it was used inside the cities, and it cannot be used for voltages higher than 20 kilovolts because it cannot have the cross arm spans, and it cannot support the higher voltages more than 20 kV. It is to be suitable, it should be treated, because a lot of problems with in case of the ground level, because once it is because it is with the wooden, it's with the wood, and there is always a chance that it may get rotten, and that has to be treated properly with the chrysolite oil, and then the portion below the ground level has to be protected well from the germs, and then the small it should be protected from all kind of weather soil conditions. So the lifespan of this wooden pole is only 20 to 25 years, because it's a very small life that it can offer, because of the termite problem and all other problems, it will decay into the nature, and then it cannot offer strong support to the overhead transmission lines. So it requires it attracts the higher maintenance cost also. So now the wooden poles are mostly removed from even the rural households. Because of the lesser life of wooden poles, we have moved on to the steel poles, where steel poles offer the good mechanical strength, and it offers the longer life. It can hold the longer spans also, so it can hold the cross spans very effectively. And generally it is used for the distribution purposes in cities. It need to be either painted, or it need to be galvanized, so that it will not rust, and then it will not go through the corrosion process, and then it can give the longer life. And there are three types of steel poles. They are rail poles, tubular poles, and then the third one is the rolled steel joints. Normally, we see these days that the tubular poles are used for the erecting the transformers and then the distribution sites inside the city, because it will not affect the aesthetics of the city, and then it will give a good feel, and then it will not alter, or it will not affect the feel and the good the look of the city. So compared to the steel poles, we have moved on to another type of poles, which are called as RCC poles. Because this RCC poles offers longer life, it is very popular, easy to construct at the site, and it offers the good mechanical strength. It permits the longer spans and then the steel poles, and it attracts very little maintenance. It gives the good outlook, and then it has got good insulating properties. This can be used for the single circuit or the double circuit lines, and then the main drawback of in the transportation cost of the poles to the site, and hence they are manufactured at the site as far as possible. So now coming to the another fourth type of the towers, they are called steel towers. You can observe that there is a difference between the steel poles and then the steel towers. In practice, the wooden RCC and then the steel poles are used for the distribution purposes, whereas the steel towers are used for the higher voltages, and then particularly wooden RCC and then the steel poles are used for the lesser voltages, that is the low voltages up to 11 kV, whereas the steel towers are used for the higher voltage transmission, and they offer good mechanical strength, longer life, and then it permits the use of longer spans, and then it can hold the line without against the loads, might be against the wind pressure, and then it offers a very good mechanical strength to the conductors, and then the overhead structure, and then the overhead accessories, that whatever that is provided. And here the protection against the lighting could also be provided, and the most importantly, the protection against the lighting is given by driving the rods into the ground. So automatically the entire structure is going to be protected against the lighting system. So it can be used for both the single circuit as well as the double circuit. Now, what is the importance of the sag? We have observed during the summer season there will be lot of sag of the overhead transmission line. So now overhead transmission line has the tendency to sag down when they are suspended between the two different poles. We can see that in the normal experiment also, if we suspend a line between the two supports, it will sag. If at all it is tightened to a larger extent, then there will not be any way that it can expand due to the temperature, and it tends to break because it is out of the elasticity. So hence what we need to understand is that it is the importance of the sag. So let us understand there are two poles, and then the wire is suspended between the two tips of the poles. Let's consider this as a support 1, and then let's consider this as a support 2. The shape of the conductor, shape of the sag depends on the distance between the two poles as well. So overhead lines shows the tendency to sag down when they are suspended between the two parts, and then it takes a shape of the catenary or a parabola. The sag plays a very important role here, and the sag which is going to play a very important role is in terms of the mechanical design of the overhead transmission lines. So from the economic point of view, the transmission lines are designed to have to attract the lowest cost, and the length of the transmission line must be around L as shown in the figure. So let's consider if the wire sags, there is an additional height of the tower that is required, which increases the cost. Because when we see normally, if there are two poles across the road, then one on the other side of the road, and then one pole on the other side of the road, and if the transmission line is passing and then it is getting connected to the other pole on the other